All right, so I have a simple Brayton cycle with a pressure ratio of 8. I've got my diagram here. I know that I've got T1, T3, and the pressure ratio. I want to find the thermal efficiency, the back work ratio, T2, and T4. You'll make air standard assumptions, so it's an ideal cycle with the exception that isentropic efficiency of the compressor and the turbine are both less than 1. Also making the assumption that it's steady state and changes in kinetic and potential energy are negligible, which means that my first law breaks down very nicely to maybe a Q in or a Q out or a work in or a work out and some delta H's. And then also you'll notice that the P2 and P3 and P1 and P4 are equal to one another. That comes from the fact that it's an ideal cycle and there's no friction. And so there would be no pressure drop in the lines. Okay, so I'll get my governing equation, thermal efficiency, work net out over Qn. So the work net out, work out is H3 minus H4, and then work in is H2 minus H1, and the Qn is H3 minus H2. So if you need help figuring out where that came from, it came from applying the first law to each of those devices. If you need a little refresher, please go back and watch the simple Brayton cycle video. Or I could put that in terms of 1 minus Q out over Q in. So Q out is between 4 and 1, and that's where you're modeling the exhaust process, and Q in is between 2 and 3, and that's how you're modeling the combustion process. And then the back work ratio is just the work of the compressor over the work of the turbine, work output of the turbine. Okay, so got those guys, and now I'm ready to solve for my H values. So H1, just pulling that right off the table at the given T1. And then state 2, well, I got to figure out what state 2S is. So I've got this isentropic efficiency, which tells me how I deviate from that ideally isentropic compression process. So I need to figure out what that H is at the end of the isentropic process, then use my efficiency to figure out what it is for the actual process. So talking about the isentropic process first, I apply an isentropic relationship. I've chosen the one in terms of pressure ratios as opposed to specific volume ratios, just because I know something about those pressure ratios, that pressure ratio. Get my PR1 value to plug in there, and that's evaluated at T1, and I just solve for PR2. I can also get the H2S, which I'm going to need in just a second. So this is not the H value that I'm going to use in my thermal efficiency and backwork ratio equations. It's this ideally isentropic, at the end of the ideally isentropic process. So H2S 544.34, but I'm going to use that H2S to figure out what the H value is at the end of the actual process. And I'm going to plug that into my isentropic efficiency equation for the compressor. It's the isentropic work over the actual work. So small number on top, big number on the bottom. Ideally, the small number, you wouldn't have to put in a lot of work to that compressor, but in actuality, you have to put in more because you're working against friction and that sort of thing. So irreversibilities within your system. So that's the number on the bottom. And I solve for my H2, I get 605.21, and of course I need my T2 value as well, and I just interpolate off the ideal air tables for that guy. Now I'm on to state 3. I have T3, so I can get my H3 value. Just read that off the table, off of table A22. Go on to H4. So once again, I've got this isentropic efficiency for the turbine that I'm dealing with, so I need to figure out what H4 is at the end of the ideally isentropic process, then use my efficiency to figure out what it actually is. So I'm going to use my isentropic relationship. So PR4 over PR3 equals P4 over P3. But I know that P4 and P1 are equal to one another, and P2 and P1 are equal to one another. So that means that P4 over P3 is just the inverse of my pressure ratio. So I go ahead and pull off the PR3 off my ideal air table so I can solve for PR4. And then I can get my H4S value. So that's at the end of the ideally isentropic expansion process. Then I use my isentropic efficiency equation for the turbine. So big number on the bottom, small number on top. Big number would be ideal case. You get a lot of work out of that turbine, and the smaller number is what you actually get due to irreversibilities within your system. And I can solve for my H4. So that's what the H value is actually at the end of that expansion process. And then I can look at my ideal air tables and interpolate for T4. And then when I plug things in, I get 26.6% for the thermal efficiency and 59.1% for the backwork ratio. All right, well, I hope that was helpful. Thank you for watching, and let me know if you have any questions.